Okay, so we will look at as a separate module community detection, but again, so there are different ways we can, different algorithms available to find out communities in a graph. And one approach of for community detection is to use the eigenvalues and eigenvectors. So that's why we are looking at this topic also in this module. So as you might have seen in the syllabus, we are going to look at a separate module on community detection algorithms. We are going to see a number of such algorithms for community detection. And since we're covering eigenvalues, we'll see kind of one approach for community detection in this module. So first of all, again, what is a community? Okay, so this is something could be new for you as a terminology. So a community in a social network, typically social networks, it could be also observed in other networks too, but we tend to do community detection more for social networks, is a kind of grouping of the vertices such that there are more edges among vertices within the community and there are relatively few edges connecting vertices across two communities. So here I have a graph. It's a connected graph, so all vertices are reachable to each other. But you can see there are more edges among these vertices that are colored green, okay, and there are more edges among vertices that are colored blue, and then more vertices among these vertices that are colored, say, orange or whatever color you want to call it. So we can say these three sets form three communities. So this is one community, this is another community, and this is another community. And also you see there are very few edges between vertices across two different communities. Okay, so there are not many edges across vertices between vertices in two different communities, and that's what you see in real world too. In real world, you say there is a community, among students. It depends on like who frequently is talking to whom, right? So you don't say people who don't really talk with each other are part of one community most of the time. Okay, so in a community, people really do have more interaction with each other, and that's what you want to find out or capture given a social network of users like this. So even think about this as your Facebook network. Okay, so these are like the people who are in your Facebook list of people, and it is possible that this person also knows this person, okay, and this person knows this person. But you see, this could be the group of people who you know from your workplace. This could be the group of people who you know from your school days. This could be a group of people you could know from your family links and so on. So it's very difficult to expect a link between, say, people who you work with, people who you know from school days, okay, and similar school days with family people. There might be some links. Who was studied with you might continue with you for working. Who studied with you might be part of your family too, but very few links to expect between two different communities like this. And that's what we would like to have. In order to call these groupings of vertices as a community, there should be a lot of links, and we'll later in the community detection module look at those terminologies, but let me just introduce them here. So something called intra-cluster density is expected to be high and inter-cluster density is expected to be low. So for a good what is called modular community, modular means you're going to look at this metric called modularity. So for a good community, that's what we mean by a modular community. Good means not like the character of the people, it's just like in order to say that's a good, that's a more what do you call, the partitioning is kind of capturing the essence of a community from a graph theory point of view. If it is having a high intra-cluster density, that means there are a lot of edges connecting people within the community compared to very few edges connecting people between two communities. And communities can also be called clusters. Okay. Now you wouldn't say something like this. Say for example, I have a figure here. That's a good thing to look at. Let me Okay, 7541. Okay, we can use this. Okay, there's edge here. I'm trying to motivate this idea of community. Else you can have there's an edge between 5 and 3, of course. There's an edge between 1 and 2. So as you can see, as I'm drawing, what I'm trying to do is, if I claim that 1457 is one community, 1457 is one community of vertices, and the other 4 vertices form another community. I don't know why this thing came up. Alright, so these colored in green, let us say, are in one community, and this colored in white or in say another community. Doesn't make really sense to call this as 2 different communities. Okay, why? You see that the black edges, or the edges that are between among users within the community. So these 4 people have only these 3 edges among them, and these 4 people also have just these 3 edges among them. Whereas you see there are more edges across or between people in these 2 communities, the red colored edges. Okay, so it really doesn't fit within this characteristic I just mentioned. So if you want to call the partitioning to be really modular communities, you expect it to have the clusters or the communities to have a high intra-cluster density and low inter-cluster density. You see here the intra-cluster density within the cluster, within the community, you have few edges. It's not high, it's kind of low. Compared to the inter-cluster density, there are more edges between the communities. So that should not be the case. If there are more edges between 2 different communities, it's good, as well as you can put all those vertices as one single community. Why we need to partition them as 2 separate communities? Doesn't make much sense. So that's why, so this is not a good partitioning of a graph into 2 communities, whereas this is a good partitioning of a graph into 2 communities, because if you now try to connect these vertices using inter-cluster edges, there are going to be relatively few edges connecting the 2 clusters, whereas there are going to be more edges within each cluster or community. Okay, so cluster, community, even you may sometimes say component, but I wouldn't say component in its pure term here. So let us use this cluster or community. They are interchangeably used. Okay. So a good community detection algorithm should find communities like this compared to communities like this. Okay. So what we are going to do in this module is look at 2 things. One is how to quantify how good is the partitioning of a graph into communities. Okay, and for that we are going to compute what is called the modularity scores of the communities, and then use the eigenvalue eigenvector approach to compute do the community detection and compute the modularity scores of that partitioning. Okay, so let us do one at a time. So let me, when we can, okay, we have time. Okay, so what is, any questions so far about communities? We just talked about intra-cluster, inter-cluster density, and kind of at the very qualitative high level. So we have not yet gone into the math. Okay, so let us look at some math now. Okay, so you want to come up with what is called the modularity score. So once you run some community detection algorithm and find out the communities of a graph, of a network, we want to quantify how good is that partitioning of the graph into communities. As I said, this is not a good partitioning, this is good partitioning. So how do we quantify that? So for that, you're going to compute the modularity score of the communities. So to get the modularity score of the communities, we are going to find the modularity score for any two pairs, any two vertices as a pair in the community, in the graph. Sorry, any two vertices in the community. Actually, yes, I'll take it back. So we are going to find the modularity scores for any two vertices within the community, but based on the information from the graph. So what it really means. So let's go through something in more detail now. So for any pair ij, okay, I'm going to compute this number. So it is the entry for that pair in the adjacency matrix, okay, minus the degree of the two vertices ij divided by 2 times the number of edges. This is the total number of edges in the graph. Okay. So what does this give you? Now this second term, okay, so this second term gives you what is called so this product of the degrees divided by 2 times the number of edges will give you the probability that there could be an edge between the two vertices I and j. Okay, so the second term gives you the probability of an edge between two vertices I and j. Is that clear? Now this entry in the adjacency matrix will be a 1 if there is really an edge between I and j. So if there's an edge between I and j, the total, the sum of these two terms, which is like this, of course, is a minus. So it's going to be 1 minus of this. Now the second term is a probability. So this product of the degrees divided by 2m, and again m is the number of edges, the total number of edges in the graph, is going to be always less than or equal to 1. Okay, so 1 minus of something less than or equal to 1 is going to be a positive quantity. It's 1 minus something less than 1, so it's going to be greater than 0. Okay. On the other hand, if there is no edge between I and j, this entry in the adjacency matrix for ij is going to be 0. Now 0 minus fraction, right? So this second term is going to be a fraction because it's a probability. It will always be less than or equal to 1, so most likely it's going to be less than 1. So 0 minus some fraction is going to be still a negative number. So if there is an edge between two vertices, so now let us look at these numbers here. So let us say we have this graph and some algorithm has recommended this as a partitioning of the graph into two communities. So what we are going to do now is look at this community of vertices 1, 4, 5, 7 and consider all possible pairs of vertices that are part of this community. So you can have 1, 4, 1, 5, 1, 7, 4, 5, 4, 7, 5, 7. So for 4 vertices, these are the 6 possible combinations. Now just for ease of doing the math, of course you can mix these pairs as long as you know whether there is an edge between them or not. So these are the 3 pairs that have an edge between them. So the entries in the adjacency matrix is a 1. So the modularity score for this pair is going to be 1 minus the product of the degrees of these two vertices. So to get the degrees of these two vertices, you have to look at the given graph, not at this community. You have to look at the entire graph and find out the degree. So for node 1, the degree is 3, and that's what I have indicated here, the degree of node 1. For node 4, the degree is 4. That's what I have indicated here. For node 5, the degree is 5. That's what I have indicated here, and so on. So that's why I said you need to find the modularity score for the vertices in the community based on the actual original graph. Okay. And again, so it is for 1 and 4, the degrees are 3 and 4. So the product of the degrees divided by 2 times that 15 is nothing but the number of edges in this graph. And the first module I mentioned a couple of approaches to find the number of edges. One approach is to sum all the vertices, the degrees of the vertices. So if you sum all the degrees of the vertices, in this case you will get, I'm not sure, I'll have to do the calculation. So these are the degrees, right? So it is 7 plus 12 plus 15 plus 19 plus 322, 27, 30. So 30 is the sum of the degrees of the vertices. Divide that number by 2. So sum of the node degrees divided by 2 will get you the number of edges in the graph. So so it's the product of the degrees divided by 2 times the number of edges. So that's as good as telling the sum of the node degrees, because we are dividing the sum of the node degrees by 2, right? So either way, it's 2 times the number of edges. So as I said, this second term is going to be a fraction. So it's, in this case, it's 12 divided by 30, right? So that's going to be 0.4. So 1 minus 0.4 is 0.6. That's the modularity score for this pair 1, 4. Similarly, for the pair 4, 5, the modularity score is 1 minus. Why it is 1 minus? Because 4, 5 have an edge between them. For 1, 4, it was 1 minus because they have an edge between them in the given graph. So it is 1 minus the product of the degrees. For 4 and 5, the degrees are 4 and 5. So also the degrees. So 4 times 5 divided by 2 times. So the denominator is always the same, 2 times the number of edges. The numerator is what varies in the second term, depending on the degrees of the 2 vertices that are part of the calculation. For vertices, for the pair 5, 7, the degree of vertex 5 is 5 and 7, it is 3 in the original graph. So it is 3 times 5 divided by 2 times 15, 1 minus of that. Now for these pairs 1, 5, 1, 7, 4, 7, they don't have an edge between them in the given graph. So it's going to be 0 minus. So because the formula is whatever the entry in the adjacent symmetries. So it's going to be 0 minus the product of the degrees divided by 2 times the number of edges. So we're going to get negative numbers. Okay. So once you get the modularity scores of the pairs of vertices that are part of a community, add up all the modularity scores. You will get in this case 0.23. So that is the modularity score for this community 1, 4, 5, 7. Do the same approach. Using the same approach, you can compute the modularity score for this community 2, 3, 6, 8. So you write down all possible combinations of vertices of these 4 vertices. So 2, 3, 2, 6, 2, 8, 3, 6, 3, 8 and 6, 8. So these are the 6 combinations. And these 3 pairs have an edge between them. So it will be 1 minus the product of the degrees. For 2 and 3, the degrees are 3 and 4. So again, vertex 2 has degree 3 and vertex 3 has degree 4. So that's why it is 3 and 4. Divided by 2 times 15, so that's going to be 0.6. So likewise for 2 and 6, again based on the original graph, the degrees are 3 for 2, for 6 it is 5, so it's 3 times 5 divided by 2 times 15, so it's 1 minus of that. So these pairs don't have an edge, so it's 0 minus the product of the degrees divided by 2 times the number of edges. So it's just coincidental for this community. In this case, you also get 0.23. It need not be always the case. You could get different numbers. Now sum up the modularity scores of the 2 communities. That's the total modularity score for this partitioning for the 2 communities put together, 0.46. Now do the same kind of calculations for this partitioning. So let us say some other algorithm has run the community detection on this graph and came up with this as the partitioning of the graph to 2 communities. So let us find out the modularity score of these 2 communities put together. So 5, 6, 7, 8 are part of one community and 1, 2, 3, 4 are part of the other community. So among 1, 2, 3, 4, the different pairs are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So you see 5 out of the 6 pairs have an edge between them in the given graph. So the calculations are going to be like 1 minus of the product of the degrees divided by 2 times the number of edges. So we're going to have more positive entries for the modularity score and just one negative modularity score. So the sum of all the modularity score is going to be reasonably larger. We get 2.67. And do the same kind of calculations for 5, 6, 7, 8. You can see they really have edge between any two vertices in this case, in this community. And there's a special name for this, it's called a clique. So we can call a community as a clique if there's edge between any two vertices that are part of that community. So it's called a clique. So even in common day, in a day to day, we say they move, those people move together as a clique. That means they always move together and talk with each other. So in this case, since all pairs of vertices have an edge between them, is all going to be 1 minus. So it's all going to be positive modularity scores. And the sum comes out to be 2.87. So now the sum of the two modularity scores is 2.67 plus 2.87 is 5.54. That's the modularity score for these two communities put together. So now looking at the numbers, you see 0.46 is much smaller compared to 5.54. So given two algorithms, one algorithm, community detection algorithm, has come up with this as the partitioning. The other one has come up with this as the partitioning, basically the set of vertices that are part of the communities. Then you will run the modularity score computation, the procedures like we just did, and come up with the modularity score for first a pair of vertices within a community, and then add up such modularity scores for all the pairs of vertices within the community and come up with what is called the modularity score for that community, and then add all the modularity scores for the different communities, and you'll get the total modularity scores for all the communities put together, and compare the two numbers and then decide which. So it makes sense to pick up these two or this as a good partitioning of the graph into communities compared to this. So that's the way you will analyze how good is a partitioning of the graph into communities. Okay. So any question on this? How to use the modularity score approach? Now, if you look at the, I'm not sure in, let me just check it. I think I might have done it. Okay. So if you look at the zip files I have posted in the course under modules, I would have posted a zip file for the pairwise modularity. So you may be wondering, do we have to do this calculations for the different pairs and all those stuff? No, from exam point of view, I will most likely not ask you to do the calculations for each pair, but you should know where the numbers are coming from. So this is the math behind the numbers for the modularity score. So I have given you a program, a jar file that will compute for you the pairwise modularity score. Okay, so let us unzip it and show its execution, and with that we can stop for today. Okay, so it's getting those files running somewhere. Okay. All right. So again, it's going to have a jar file. I have named it pairwise modularity. Now, so what you need to get the pairwise modularity scores. So again, type up the adjacency list. We'll do that for this graph. So 1 space 2 or 1 tab 2, either way is fine. 1 3, then 1 has edge with 4. Then those are 3 edges for 1, then 2 has an edge with 3, 2 has an edge with 6, 3 has edge width 4, 3 with 5. So always just look at the higher ID for the other end, because lower ID is already captured somewhere earlier. Then 4 has an edge width 5, 4, 6. 4, 3 is already captured as 3, 4. So by now you should be able to come up with that distance list. Then 5, 6, 5, 7, 5, 8, 6, 7, 6, 8, 7, 8. Now you can count the number of edges. That's going to be 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 edges. So let us save this to a text file. Some name, as long as you can keep track of it. Okay, so you can have more than one executable open at a time, that's fine, but I'm just closing my previous execute. So double click on this pairwise modularity executable jar file and load that text file that we just saved. Modularity graph. Okay, so once you load it, double click on it, it will do the calculations and it will display all the pairwise modularity scores. So it will display just based on the node ID. So for 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8. Now one thing you could notice here is it considers all possible combinations. So it doesn't just look at the edges, okay, in the graph. So it looks at all, because sometimes you may come up with this partitioning where there'll be a lot of pairs that don't have edge between them. So that's why the code looks at all possible combinations of vertices. So if the pairwise modularity score for a pair is positive, that means actually they have an edge between them, because the calculations is like what? 1 minus of the product of the degrees by 2 times the number of edges. So that's going to be positive only if there's an edge between the corresponding vertices. It's going to be negative if there's no edge between them. So it's going to be 0 minus the product of the degrees by 2 times the number of edges. So it's going to look at all possible combinations of vertices that are in the given graph. So 1, 2, 1, 3 up to 1, 8. Then 2, 3, of course 2, 1 is already considered here for as 1, 2. So that's why I don't print 2, 1. So 2, 3, 2, 4 up to 2, 8. And then 3, 4, 3, 5, 3, 6, 3, 7, 3, 8. And so on. So it's 7, 8. So these are the different possible pairs of vertices in the given graph. So now what you can do is, once you're given that, say for example these are the two communities, you know the vertices that are part of the community. So in this case say 1, 4, 5, 7, then go ahead and list down all possible combinations of the vertices within that community. So it is 1, 4, 5, 7. So we are going to have so if it's 1, 4, 5, 7 are the vertices that are part of the community, so write down all pairs. So it's 1, 4, 1, 5, 1, 7, 4, 5, 4, 7, then 5, 7. Then based on this output, pick up the scores. So 1, 4, the score is 0.6. 1, 5, the score is negative 0.5. 1, 7, the score is negative 0.3. 4, 5, somewhere down, the score is 0.333. 4, 7, it is negative 0.4. 5, 7, it is 0.5. So these are the pairwise modularity scores for this pairs in this graph. So now add up these numbers, and these are the numbers you would have got in your calculations too. So 0.6, 0.33 for 4, 5, for 5, 7 it is 0.5, for 1, 5 it is negative 0.5, for 1, 7 it is negative 0.3, for 4, 5 it is 0.33, 4, 7 it is negative 0.4. So the same numbers, I'm not showing anything new. But instead of going through this math, the program does this for you. And all you have to do then is add these numbers and say that's the modularity score for this community. Okay. So I suggest you to try this out and make sure you're able to run these two graph files and get the modularity scores and go through the same kind of calculations. So next time what we'll do is we'll use the eigenvectors approach to do some community detection, to partition a graph into communities and then come up with the modularity score of the communities. Okay, and so this is a hierarchical approach. We'll start the entire graph as one community, keep partitioning it. So there will be a scenario where we have to decide, like, so this is like the hierarchy. So we'll start the entire graph, we'll have to keep partitioning it to communities, but we have to decide whether we should stop with 0, 3, 4, 5 and 1, 2, 6, 7, 8, 9 as two communities of the graph, or do we have to look at 0, 3, 4, 5, 1, 2, 8 and 6, 7, 9 as three communities of the graph. So where we have to kind of prove or cut this tree, the hierarchy, and consider that as the partitioning, and for that the modularity scores are going to be helpful. Okay, just by looking at the numbers, let's take 30 seconds. So if you consider these two as communities, the corresponding modularity scores you can see come out to be 2.67 and 3.13 for this graph. So the sum is like what? 2.67 plus 3.13 is 5.8. Whereas if you consider these three as the communities for the graph, these are the modularity scores. So 2.67 plus 1.9 plus 1.83 is 6.4, greater than 5.8 something we got by considering these two as the communities. So that means you will be now able to say, instead of considering 0, 3, 4, 5 and 1, 2, 6, 7, 8, 9 as the two communities of this graph, it makes more sense to consider these three as the communities of the graph based on, and all these three are again found by the eigenvector approach, but using the modularity scores we'll be able to decide where to cut the hierarchy and say that's the partitioning of the graph into communities. Okay, so we'll go through all these things next time. Okay, so right now make sure you're able to get the pairwise modularity scores for a given graph and go through these calculations that I have given here. Alright, so that will stop with this. So any questions?
Dr. Mike, I
Yes.
have one question, but it's about the last lecture.
Okay.
In the part of a small world